Laplace transform of f times the Laplace transform of g. Or to write it out in the more explicit notation, where we show what everything is a function of. Find a different marker. This one clearly is. Then writing it this way, the Laplace transform of product f and g is not equal to the Laplace transform of f of t times the Laplace transform of g of t. So again, and you might have guessed that this was true because, for example, when we have the Laplace transform of a sum of two functions, like the Laplace transform of the quantity f plus g, that was equal to the Laplace transform of f plus the Laplace transform of g. So you might have thought that the similar thing would be true for multiplication, but like I said, it's not. The question I want to ask, though, is, even though this is true, or not true rather, is there something similar that's true? And the answer is yes. And in particular, this one's not good either. There is, in fact, a useful expression for something like the right-hand side of this. And if we have the Laplace transform of the function f times the Laplace transform of the function g, there is something that is useful as another way of writing that. It's not obviously the Laplace transform of f times g, but let's see what it is. Okay? So, the purple one. Let's try this blue one. Okay, so let's make the following definitions. Let's let the function g of p denote the Laplace transform of the function little g of t. Right? Our usual notation is we'll use a lowercase letter for the function whose Laplace transform we want to take. Remember, it's a function of the variable t, and then we'll use the same letter in capital version for the Laplace transform of that lowercase function, and of course it's a function of a different variable p. Okay? So by definition of the Laplace transform, remember that this is the integral from 0 to infinity of the function little g of t times e to the minus pt dt. Okay? And similarly, let's let capital H of p be the Laplace transform of little h of t, which is, again, by definition of the Laplace transform, the integral from 0 to infinity of h of t times e to the minus pt dt. Okay? So then the Laplace transform of g times the Laplace transform of h, right? So we're using g and h as the names of our two functions, not f and g like we used over here. In other words, this is capital G of p times capital H of p. So let's write out the integrals for this, right? So capital G of p is the integral from 0 to infinity of little g of t e to the minus pt dt. And actually, I'm sorry, for reasons that will become obvious in a moment, I'm going to do a change of variables at this stage. Instead of calling this t, right, g of p is this integral right here, but t is the dummy variable of integration here. Right? And again, since it's a definite integral, when we evaluate this integral at the limits, it will no longer be a function of t. So obviously we could call that variable t anything we want. And since I'm going to plug both this expression and this expression in for the capital G and capital H, I would rather change names of the variables in both of those integrals, actually. I certainly don't want to use the same variable for both of them, and it's going to be more convenient to change both of them. So in the expression for capital G of P, let's replace t by the Greek letter sigma, okay, as the variable of integration. And in this integral, when I substitute it, let's replace t by the Greek letter tau, okay? So in capital G of P, it'll be an integral from 0 to infinity of G of sigma times e to the minus p sigma d sigma. Right? That's for capital G of P. And then for capital H of P, we've got the integral from 0 to infinity of h of tau, right? Replacing t by tau, times e to the minus p tau d tau. Okay, we've used tau or d tau as a volume element before, but that's of course not what I'm suggesting here. It's just, you know, some variable. So anyway, we've got the product of these two integrals right here. And so let's move this integral sign out in front. Right? We're integrating over tau here, but there's nothing in front of this that depends on tau. So we can move this integral sign out in front. So we've got both integrals out in front with limits from 0 to infinity. And then let's combine the integrands. Right? We've got an exponential here and an exponential here that are multiplied together. So that means we can add the exponents and combine them. So we'll have e to the minus p times the quantity sigma plus tau. Right? And then we'll have a g of sigma and an h of tau. And we are integrating then over both sigma and tau. Okay? And then let's put parentheses like this. Right? We could imagine doing the sigma integral first, the innermost one, and then the tau one later. Okay? So let's do another change of variables at this point. In the sigma integral, right, the innermost one, the one that we are doing first as indicated by those parentheses, in that sigma integral, let's change variables. Let's let t be equal to sigma plus tau. Okay? And of course, I had previously used t as a variable up here, but I had changed t to sigma on one and tau on the other. And the reason I did that actually in both of them, again, I certainly didn't want to use the same symbol in both of them when I substituted down here. But the reason I changed both instead of leaving one as t is because I wanted to reuse t at this point and redefine it this way. Okay? So anyway, when we're doing that first integral, the sigma integral, remember that as we're doing that integral, we are still holding tau constant. Right? We're not letting tau change and vary over its range from 0 to infinity until we do that second integral, the tau integral. So we're still thinking when we're doing this first integral of tau being held constant. And so that means if we do this change of variables, we define t as sigma plus tau, with tau being constant, it means dt and d sigma are equal. Okay? So anyway, so let's do that change of variables then. So the Laplace transform of g times the Laplace transform of h, or in other words, capital G of p times capital H of p, is going to be equal to, okay, so we've got our outer integral from 0 to infinity, and then our inner integral, come back to the limits on that in a moment, but t is defined as sigma plus tau, and that's what's in the exponent here, so the exponential becomes an e to the minus pt. and our function g, which had sigma as its argument here. Sigma is t minus tau, so that's the new argument written in terms of our changed variable. H of tau stays as it is. And then the d sigma is replaced by dt. And that's the inner integral, and then we still have the d tau for the outer integral outside the brackets. Now let's think what these limits are. They're not 0 to infinity anymore. Right? Our old limits reflected initial and final values of sigma. Our new limits, since we're now integrating over t instead of sigma, have to show the beginning and ending values of t. Okay? So on the lower limit, we had sigma equals 0. And when sigma equals 0, we can see from this relationship here that t will be equal to tau. Right? And for the upper limit, sigma was equal to infinity. And when sigma is infinite, of course, t is infinite also. Okay, so our new limits on this first integral here will be from tau to infinity. Now, let's visualize what kind of geometrically, what region we're integrating over as we do this double integral right here, right? And in particular, let's look at this. I'm going to try the purple marker because this blue one's light also. Let's draw a graph where we put tau on the vertical axis and t on the horizontal axis. Okay? So let's think about, in that tau t plane, what we're integrating over as we do this integral. So the first thing we do the dt integral. That's the inner one. And we're integrating from tau to infinity. In other words, t starts at the value tau and ends at the value infinity. Right? Whereas these were limits on tau. So in other words, the lower limit is defined by a line in that plane, right? Line tau equals t. Is a line of slope 1 that starts at the origin, right? And so as we do this integral right here, we're letting t go from tau to infinity. And remember, we're still holding tau constant when we're doing this first integral. We don't let tau change until we do the second integral. So in other words, for a fixed value of tau, like a fixed point on the vertical axis, what we're doing is we're letting t start at the value of tau and go to infinity. In other words, we are starting along this line, right, where t equals tau, and we are going to infinity off in that direction as we do this first integral. Okay? So in other words, think of maybe, if you want to think of this as sort of like a Riemann sum kind of thing, right? Think of maybe a little range here, d tau, along the tau axis, and we're integrating, and we're getting that little area of that little strip right there. Then when we do our second integral, our integral over tau, we're letting tau go from 0 to infinity. So on the tau axis, in other words, we're starting down here at tau equals 0, going all the way up to tau equals infinity. In other words, as we do that, we're including this strip, and this strip, and this strip, and this strip, and so on. So it's sort of like a Riemann sum, except it sort of turns sideways, right? And usually you think of the Riemann sum as consisting of vertical bars, not horizontal bars like that. But in any case, we could say that this integral is over this shaded area In other words, this triangle in the first quadrant located under the line tau equals t. Right, that's sort of a triangle that goes off to infinity in that direction. Well, we could cover that area in a different way, other than doing it that way. So we could, in other words, change the order of integration in this integral. Instead of doing the t integral first and then the tau integral, we could do vice versa. Do the tau integral first and then the t integral afterwards. But when we do so, we need to be careful that we are integrating over the same region in that tau t plane that we were originally. So in other words, we have to be careful about the limits when we do this order of integration. Okay? So in other words, what we're doing, again, if we look at a graph on the tau t plane, here's the line tau equals t. We want to integrate over the area underneath that line. That's what I call the triangle. But instead of imagining little horizontal strips that we combine like this, imagine little vertical strips that we combine. Right? That one, plus that one, plus that one, plus this one, and so on. Right? So, then our tau integral, the one that we do first, right? So imagine, as we're doing this tau integral, t is held fixed. So we're looking at a fixed value of t. That means a fixed point down here on this axis. And to cover this region then, tau, the integral we're doing first, tau has to go from 0 to t, right? To cover this whole extent right here. So the tau integral will run from 0 to t, and then the t integral, okay, we're letting the tau integral go from 0 to t. We've done one of these little columns right there, and then to combine with the rest of the columns, t has to run from 0 to infinity. Okay? So, let's write then our expression after we've done that change of order. The Laplace transform of f times the Laplace transform of g. In other words, our function capital G of p times capital H of p will now be equal to, right, the second integral, the one I'm going to leave outside, is for t, and we said it's going to run from 0 to infinity. And then in square brackets, we'll put the inside integral, the tau integral, which we said runs from 0 to t. Right? And in the integrand, we've got an e to the minus pt. And we've got a g of t minus tau, and an h of tau, and a d tau, and then outside the square brackets are dt. Well, let's make one change in this. Let's pull the e to the minus pt out in front of the first integral. This does not depend on tau, right? So as far as the tau integral is concerned, it's a constant and can be pulled out in front. So let's do that, and then in the square brackets, we'll leave the integral from tau equals 0 to infinity of g of t minus tau times h of tau d tau. and then the dt outside the parentheses. Well, this looks like a Laplace transform again. Remember the definition of a Laplace transform? We can actually refer back to it right over here. Laplace transform of the function g of t, we multiply it by e to the minus pt and integrate over t from 0 to infinity. So, in other words, this right here looks like the Laplace transform of I'm sorry, I did screw up the limits here, didn't I? Tau went from 0 to t. Okay, so I wrote that limit incorrectly. So anyway, this looks like the Laplace transform of the integral from 0 to t of g of t plus or t minus tau, h of tau, d tau. The Laplace transform of that whole thing. Right? That whole thing is what's in the square brackets here. So we take that whole thing, we multiply it, right? This is some function of t, because when we finish doing this integral and evaluated the limit, since the upper limit is t, the result will be some function of t. We're taking that function of t, we're multiplying it by e to the minus pt and integrating over t from 0 to infinity. That's the definition of a Laplace transform. So this is actually the Laplace transform of this quantity in the square brackets right here. Okay? So anyway, let's define this quantity to be something we'll call the convolution of two functions g and h. We'll define the convolution. First of all, we'll write it. This is the notation for convolution. It's a g star h, okay, like a star or an asterisk. It kind of describes the operator. And this is going to be defined as the integral of g of t minus tau times h of tau d tau with limits from 0 to t. Okay? In other words, it's the quantity that we have in square brackets up here. Okay? So this is the convolution of the two functions g and h. That's how it's defined. So with that definition, we can write our result up here as Laplace transform. I'm sorry, I wrote f and g right here, but I was calling my two functions g and h, wasn't I? So then what we have is that the Laplace transform of g times the Laplace transform of h. Right? That's the left-hand side up here. So that is equal to the Laplace transform of the convolution of g and h. Right? So that's the result we just derived. And this is sometimes called the convolution theorem. Or to be more precise, the convolution theorem for Laplace transforms. There's actually a very similar theorem, convolution theorem for Fourier transforms also, but I don't think we'll have time to get into that. This is the more useful of the two anyway. Okay, so to compare this with what we started with, again, we said that Laplace transform of, use the names g and h, the Laplace transform of g times the Laplace transform of h was not equal to the Laplace transform of the product of g and h. But what is true is that the Laplace transform of g times the Laplace transform of h is equal to the Laplace transform of the convolution of g and h. Okay? So that's what the convolution theorem tells us. This is going to be useful. Among other things, we'll see how we can use this to solve some differential equations too. It'll be sort of give us a little way of enhancing our technique for using Laplace transform to solve differential equations that we talked about last time. This will allow us to maybe solve some additional differential equations that we couldn't have done with the method that we used last time, because it gives us an extra tool. And I'll show you how to do that in just a moment here. But first, I want to just mention one other thing about convolutions. that is going to be useful to us also. You can show, and I'm not going to show this, so I'm not going to take the time, but you can show that the convolution is commutative. In other words, convolution of G and H is equal to the convolution of H and G. Or in other words, to write that out in terms of integrals, a convolution of G and H is defined right here. So, in other words, this tells us the integral from 0 to t of G of t minus tau times H of tau d tau is equal to convolution of H and G. In other words, switch the roles of H and G in the definition here. So the integral, in other words, from 0 to t of H of t minus tau times G of tau d tau. Right? Those two integrals are equal to each other. So if you're trying to evaluate a convolution of these two functions, since we know these two integrals are equal, we want to do whichever integral is going to be easier to do. And so notice the difference between them, right? The difference between what's the functions g and h here is their arguments, right? One has an argument tau, the other has an argument of t minus tau. So t minus tau is a more complicated argument, so it's probably going to be a simpler integral to do if we put that t minus tau argument in whichever function is simpler. Right, if g is a simpler function of its argument than h is, then this integral is probably easier to do. If h is a simpler function, this one's probably easier to do. I put the more complicated argument in the simpler function. That will make the integral easier to evaluate. So remember when we get to evaluating convolutions, which we'll do in just a minute, that we can do that. Okay? Anyway, convolutions do have some physical meanings, some applications that are interesting in physics and engineering that we'll talk about next time. Okay? But for now, let's use them to solve differential equations. And in particular, the thing that they're going to be valuable for is to help us find inverse Laplace transforms. Okay? Remember that it's difficult in general to find inverse Laplace transforms. So if we're trying to find an inverse Laplace transform, in other words, what we're trying to do is given some function capital F and P, f of P, we want to find a function little f of t such that capital F of P is the Laplace transform of little f of t. Right? If it was the other way around, if we knew little f of t and wanted to find capital F of P, we could, of course, just evaluate this integral. Right? But as I told you when we first talked about Laplace transforms, there really isn't a similar integral you can do to go in the opposite direction. Right? Unlike the case for Fourier transforms, where we do have an integral we can do to find an inverse Fourier transform, we can't do that so simply for Laplace transforms. So up until now, our usual way of finding inverse Laplace transforms has been to look in that table, right? That table of Laplace transforms at the end of chapter 8, and basically take our function capital F of P and just scan through that table to try to find it in the table. And if we find it, then we can read out from the table what little f of t is. But unless we can find it in the table, we don't really have a way of finding inverse Laplace transforms. Well, it turns out the convolution theorem gives us a way of doing that. Okay? If we can't find this in the tables. So here's our procedure. And then we'll look at an example of this. You want to factor your function f of p that you're given into two other functions of p. We'll call them g and h. Okay? And the idea is that g and h are in the tables. So we can read off from the tables their inverse Laplace transforms. In other words, little g of t and little h of t. Okay, then capital F of p, which again was capital G of p times capital H of p. In other words, the Laplace transform of g times the Laplace transform of h. I have little g and little h. Well, according to the convolution theorem, the Laplace transform of little g times little h is the Laplace transform of the convolution of g and h. Okay, using the convolution theorem. Well, we started with capital F of p here, and capital F of p is by definition the Laplace transform of little f of t. Okay? So if the Laplace transform of little f is equal to the Laplace transform of the convolution of g and h, then that means little f is equal to the convolution of g and h. Okay? And it was little f that we wanted to find, so this is how we do it. Okay? So let's look at an example of that. So let's find f of t. If capital F of p, in other words, the Laplace transform of little f of t, is equal to p over p squared minus 1 quantity squared. And this one is not in the tables. Okay? You can scan through the table looking for through those columns of the capital F of p's, and you will not see this entry. Okay? So if you needed to find the inverse Laplace transform of this function, you're stuck unless you know about the convolution theorem. Okay? Well, our f of p, in other words, p over p squared minus 1 quantity squared, what we said here is try factoring this into two other functions. So the obvious thing, it looks to me like how we could factor this, is p over p squared minus 1 times 1 over p squared minus 1. Right? We've got p squared minus 1 quantity squared in the denominator. Put one of those factors in this term, one in this term. Okay? So let's call this our g of p, and this our h of p. And those g of p and h of p's we can find in the tables. Okay? So for g of p being equal to p over p squared minus 1, the little g of t, that is the inverse Laplace transform of that, is cosh of t. That is L10 in the tables. Right? Okay, and the function capital H of p 1 over p squared minus 1, in other words. We can find that one in the tables also. It's entry L9 in the tables. And its inverse Laplace transform h of t is sinh of t. Right? Well, since capital F of p is equal to capital G of p times capital H of p, and again by the convolution theorem, actually first let's write it as the Laplace transform of little g times the Laplace transform of little h. And by the convolution theorem, we know this is the Laplace transform of the convolution of g and h. And again, this is the Laplace transform of the function little f. So little f is equal to the convolution of g and h. So all we have to do with the convolution of g and h to find our answer for little f. The definition of the convolution of g and h is this function right here. Again, we said that in evaluating it, we can put the t minus tau argument in whichever function is simpler. Well, our functions g and h are both maybe equally simple or equally not so simple in this case. One is the sinh, one is a cosh. Doesn't seem like one of those would be simpler than the other, so it probably doesn't matter in this case which we put the t minus tau argument into. So let's put it in the cosh. Right? So in other words, f of t will be equal to the integral from 0 to t of g of t minus tau times h of tau d tau. Right? That's the definition of the convolution. So let's plug in what our functions g and h are. Right? So g is cosh, but the argument is not going to be just t or not going to be just tau. It's going to be t minus tau, so it's going to be a cosh of t minus tau. And h of t is the sinh of t, but it's h of tau we want to plug in here, so it'll be the sinh of tau. And then we've got a d tau, and of course our limits are from 0 to t. Well, to evaluate this, it's probably easiest if we replace those coshes and sinh by exponentials. So let's use the fact that the cosh of x, remember, is e to the x plus e to the minus x over 2. And the sinh of x is e to the x minus e to the minus x over 2. Again, just like the definitions of cosine and sine in terms of complex exponentials, except you leave out all the i's. Okay? Both the I down here and the sine, and the i's in the complex exponential. Okay, so if we replace these by the complex exponentials, they both have a factor of 2 in the denominator, so combining those factors of 2, we get a 4 in the denominator. That factor of 1/4 can be pulled out in front. So our function f of t is going to have a 1/4 out in front, and then it's going to have an integral from 0 to t. And so from the cosh of t minus tau, we're going to have an e to the t minus tau minus an e to the minus the quantity t minus tau. Right? And again, the 1/2 I pulled out in front. And then for the sinh of tau, again, the 1/2 I pulled out in front. So we have an e to the tau minus e to the minus tau. And I think I just put in a wrong sign on one of them, didn't I? this one should be a plus sign because that's the cosh, right? Whereas the other one is a minus sign because it's the sich. Okay, and then the detail. So let's just multiply this all out. Right, so this times this. Remember when we multiply two exponentials together, we add the exponents. So that one will give us e to the t. Similarly, this one times this one. When we add the exponents, and first of all, there'll be a minus sign out front of that one, and there'll be an e to the t minus 2 tau when we add the exponents on that one. And then we have plus this times this. And again, if we add the exponents, let's see, this is an e to the minus t plus tau, and then we add another plus tau. So that's an e to the minus t plus 2 tau. And then finally, this one times this one, and that will have a minus sign out in front. See, this is e to the minus t plus tau, and then minus tau, so the tau's cancel, so we get an e to the minus t. And then there's a d tau. Okay. Well, we know how to do this integral. Right? We're integrating, remember, over tau. Okay? So this first term doesn't depend on tau, right? So this is just, think of it as a constant. What if it were 2, for example? Then the integral would be 2 tau. Right? So it's tau times e to the t. Right? Tau times this constant. Okay, this term does depend on tau. There's an exponent there. So let's see, here's the minus sign from out in front. And when we do that integral, we're going to get something that I'll fill in here in a moment. But first of all, we get the same exponential back again. And since we're integrating with respect to tau, we bring a factor of minus 1/2 out in front. Right? We divide by the coefficient of tau. Okay, similar thing for this term. This has a plus sign out in front. We do the exponential, we do the integral, we get the same exponential back again, so e to the minus t plus 2 tau. And we bring down a factor of 1/2, right, the coefficient of the tau. And then this term doesn't depend on tau, it only depends on t, but t is a constant as far as we're concerned. So similarly to the first term, we're going to get a minus tau e to the minus t. Okay, and all this has to be evaluated at the limits of integration from 0 to t. Okay, and remember, we integrated over tau, so we're plugging in these limits for tau, not for t. Okay, so let's plug in these limits, see what we get. So we got a 1/4 out in front. So from the upper limit, here we have a t e to the t. Okay. Let's do the upper limit and then we'll do the lower limit from all the terms. Okay, so in this second term, minus signs cancel, so we get a plus 1/2, and we plug in tau equals t, so t minus 2t, that's e to the minus t. From this third term, when we plug in tau equals t, minus t plus 2t gives us e to the t. And in this last term, when we plug in tau equals t, we have minus t e to the minus t. So that's all from the upper limit. And then from the lower limit, and we subtract because it's the lower limit. So now we're plugging in tau equals 0, so we get 0 from this first term. From this second term, when we plug in tau equals 0, we just get a 1/2 e to the t. From this term right here, when we plug in tau equals 0, we have a 1/2 e to the minus t. And when we plug in tau equals 0 on that term, we get 0. Okay, so let's combine terms and try to simplify this. So our f of t, we've got a 1/4 out in front. And I'm going to combine terms that sort of look similar to each other. So for example, that term I'm going to combine with that term, right? So we have a t e to the t minus t e to the minus t. Okay, we're combining those two terms. And let's combine these two terms. They both have 1/2 in them. I'll pull that out in front. So 1/2 times e to the t plus e to the minus t. And then let's combine these two down here. There's a 1/2 out in, or a minus sign out in front, and let's pull out the 1/2 there. So that's also an e to the t plus e to the minus t. Well, those and those cancel, right?
Yep.
So our f of t is 1/4 t times the quantity e to the t minus e to the minus t. Well, quantity in parentheses almost looks like a cinch again, right? If it had a 2 in the denominator, it would look like a cinch. So let's pull one of the factors of 2 from the 1/4. That'll be the 1/2 out in front. We've got a t out in front. And the other factor of 2 I'm going to put in here. And then that will look like a cinch t. So here's our f of t. Right? That is the function, that is the inverse Laplace transform of this capital F of p that we started with here. Okay? And you could verify that by taking that f of t, plugging it into the definition of Laplace transforms, calculating the capital F of p, verifying that you get this backwards again. Okay? But it's not, this is not one you can find in the table, but here's how you can use the convolution theorem to figure it out in a way. Okay, let's do our break right now, and then when we come back, we'll see how we can use this to solve differential equations. Are useful in solving certain differential equations, like I just told you. And in particular, if you have a differential equation of the form a times y double prime plus b times y prime plus c times y equals some function, we'll call it f of t, right? And we want some function y of t. We're thinking of y as a function of t rather than a function of x here. That satisfies this. So in other words, I'm using y prime to denote derivative of y with respect to t, right? Since that's what t depends on. Okay, and so if a, b, and c are constants, right? So a differential equation, obviously this is a second order differential equation, right? Because the second derivative is the highest one. It's linear because y double prime, y prime, and y are each to the first power. There's no products of any of them or anything appearing. And it's got constant coefficients, right? The coefficients of the y double prime, y prime, and y are all constants. And but it's not homogeneous, right? Because there's some function of t over here on the right-hand side. And this is especially true if we have boundary conditions where y naught, in other words, y at t equals 0, is equal to 0, and y naught prime, in other words, y prime evaluated at t equals 0, is also 0. Okay? A slight variation of the technique I'm about to show you could be used if you have other boundary conditions besides these. But these are the easiest ones to do. And so in the example I'll show you, that will be the case. Okay? So let's spell out our general technique and then we'll look at an example.
Okay, you just got the time to take a look.
So you want to take the Laplace transform of both sides of the differential equation. Okay, and you want to use table entry L35. And L35 is the entry in the table that we talked about last time. It says that the Laplace transform of y prime is equal to p times capital Y minus y naught. And it says that the Laplace transform of y double prime is equal to p squared times capital Y minus p times y naught minus y naught prime. And remember that capital Y here stands for the Laplace transform of little y. Okay? Now, if we really have the boundary conditions I specified over there, y naught is 0, so this will just become p times capital Y. And y naught and y naught prime are both 0 with those boundary conditions. So the Laplace transform of y double prime would just be p squared times capital Y. Okay? So those will be very simple, right? So we're going to plug those in after we take the Laplace transform of both sides. We're going to plug those in, and that will lead to an equation of this form, right? We have A was the coefficient of, well, let me maybe write out this first step first. Right, first we take the Laplace transform of both sides. Let's assume, again, we have something of this form. A times double prime, y double prime, I'm sorry, plus b times y prime plus c times y equals some function f of t. Okay, so we're going to take the Laplace transform of both sides of that. So we have A times the Laplace transform of y double prime plus b times the Laplace transform of y prime plus c times the Laplace transform of y equals the Laplace transform of f of t. Okay, so that's what we get when we take the Laplace transform of both sides. Then we're going to use these L35 results. So that means we can rewrite this as A times p squared times capital Y. Right? Because p squared times capital Y is the Laplace transform of y double prime. Similarly, plugging in the second term, we have b times p times y, capital Y. And in the third term, c times capital Y. And on the right-hand side, the Laplace transform of this function f of t. Okay? Then solve this for capital Y. I mean, so far this is a lot like the example we did last time, right, of differential equations. So, I mean, there's only basically one difference that comes along a little bit later. So this is an algebraic equation for capital Y. Right? On the left-hand side here, we could pull out a capital Y and write AP squared plus BP plus C quantity times capital Y, and then solve for capital Y by dividing by that coefficient. And so, in other words, capital Y will be 1 over AP squared plus BP plus C times capital F of P, where capital F of P denotes the Laplace transform of little f of t. Okay, so this is your f of p right there. So let's define this to be g of p right here. This 1 over AP squared plus BP plus C. Although your textbook actually gives it a different name. Your book calls this capital T of P. We've just used T for so many other things that I'd rather not use that letter. I think it's possibly confusing. But the book calls this a transfer function, and I guess that's what that T stands for, right, is a transfer function. But the point is, at this point, we have capital Y equals G of P times F of P. By the way, there is no need at this point to look up capital F of P. We'll see why in a minute. Okay? I'm just using it as notation for the Laplace transform of little f of t. You presumably know what little f of t is because it was on the right side of your original differential equation. And you may be able to find it in the tables, but there's no need. Okay? You don't need to look in the tables and find what it is. Okay? We'll see why in a moment. We don't need to actually evaluate capital F of P. I'm just using it as a kind of placeholder for notation here. Okay? But anyway, we've got the capital Y then is the product of two functions, capital G and capital P, capital G and capital F. So all you have to then do is to use the convolution theorem. You're trying to find little y, right? That's the solution to your differential equation. You now know capital Y capital Y is this G of P times F of P. So it's inverse Laplace transform by using the convolution theorem, because remember capital G times capital F is really shorthand notation for the Laplace transform of little g times the Laplace transform of little f. So if you can find your capital G in the tables, right? Look for your capital G in the tables of Laplace transforms and read off from those tables what the function little g, its inverse Laplace transform, is. Okay? So then, since capital Y, which is the Laplace transform of little y, is equal to the Laplace transform of little g times little f, the convolution theorem tells us that little y will be equal to the convolution of g and f. Okay? And I told you a minute ago, you don't need to look up the function capital F. You already know the function little f. It's the right-hand side of your differential equation. All you're going to have to do at the end is plug that function little f into the definition of the convolution and evaluate that convolution interval. So again, there's actually no need to look up the capital F of P in the table. Okay? You are going to have to try to find the capital G in the table, but there's no need to look up the capital F in the table. Okay? So that's the basic technique. So let's look at an example. So our example, let's say we have the differential equation y double prime minus 4y prime plus 3y equals e to the 2t. Okay? So we want some function y of t that satisfies this. Again, y is a function of t, so y prime means the derivative of y with respect to t. And let's say we have the initial conditions that y naught and y prime naught are both 0. Those are what I said would be the easiest boundary conditions to deal with. Okay? Okay, so we're going to take the Laplace transform of our ordinary differential equation. So get the Laplace transform of y double prime minus 4 times the Laplace transform of y prime plus 3 times the Laplace transform of y. Remember, the Laplace transform operator is linear, so we can do that. We can break a sum, right? When you have a Laplace transform of a sum or a difference, we can take the Laplace transform of each term separately, and any constant coefficients can be pulled out in front. Okay, so we've done that. And on the right-hand side, we have the Laplace transform of our function e to the 2t. So in other words, the f of t that we talked about generically appearing on the right side of this differential equation is e to the 2t in our case. Okay, so then we're going to use L35 in this equation right here. Okay, L35 tells us the Laplace transform of y prime is equal to p times capital Y minus y naught. And the Laplace transform of y double prime is equal to p squared times capital Y minus p times y naught minus y naught prime. And capital Y, remember, is shorthand notation for the Laplace transform of capital Y. Okay? Well, in our case, y prime, or y naught and y naught prime are both 0. So the Laplace transform of y prime is just p times capital Y, and the Laplace transform of y double prime is just p squared times capital Y. Okay, so we're going to substitute all of those into the ordinary differential equation. So that is then going to give us p squared times capital Y minus 4 p times capital Y plus 3 times capital Y, and that's equal to the Laplace transform e to the 2t. That's our capital F of t. Okay? Because again, e to the 2t was our little f of t. So if we solve this for capital Y will be equal to 1 over p squared minus 4p plus 3. And if I, on the left-hand side here, if I pulled out a capital Y, I'd have capital Y times the quantity p squared minus 4p plus 3. So I can divide by that quantity, bring it over to the other side, and then times our capital F of p. So this function right here is our capital G of p, or if you prefer the book's notation, the transfer function, capital T of p. Right? So what we usually want to do at this point, right? I said that we look for G in the tables, but I don't think we're going to find this in the tables. What you often have to do at this point, I'm sorry I should have told you this back here, is you may have to factor this. before you look for capital G in the tables. Okay? So in our case, our capital G of P was 1 over P squared minus 4P plus 3. So let's factor that. We can factor that into P minus 3 and P minus 1. Right? Because if we multiply that back out, we get a P squared, we get a minus 1P and a minus 3P combined would give us a minus 4P, and minus 3 times minus 1 is plus 3. Right? So that's our factored version of that. Okay? Then we look at our tables and we see if we can find a capital G or a capital F or capital Y or whatever they call it in the tables, a Laplace transform, a capital letter in the table, and it's a function of P that is of this form. Well, L7 I think will do it for us. L7 says that if we have a function little g of t of the form e to the minus at minus e to the minus bt all over b minus a, where a and b are some constants. Okay? L7 tells us that the capital G of P that goes along with this, the Laplace transform of this little g of t, is 1 over P plus A times P plus B. So this looks like, and this by the way is true if A and B are not equal to each other. Okay? Well, this looks like a version of this with A equals minus 3 and B equals minus 1. Right? Because then our P plus A is P minus 3, which matches up with this, and our P plus B is P minus 1, which matches up with that. Okay? And A and B are indeed not equal. By the way, if A and B had been equal when we factored this, right? In other words, right, look, this is something of this form. If A and B turned out to be equal, you would simply use table entry L8 or L6 instead of L7. L6. Okay? Okay? So anyway, then our G of t is of this form right here. We just have to plug in our values of A and B. So e to the minus at is e to the 3t. We subtract e to the minus bt, which is e to the t. Okay, plugging in b equals minus 1. And this whole thing is over b minus a, in other words, minus 3 minus a minus 1. In other words, minus 3 plus 1 is minus 2. Or no, it was b minus a. I did a minus b. Okay? So b minus a is minus 1 minus a minus 3. In other words, minus 1 plus 3 is 2. So the plus 2, not minus 2. Okay, so that's our little g of t. And remember, our capital Y, which was shorthand notation for the Laplace transform of little y. Little y is what we want. It's the solution to our differential equation. Our capital Y was the product of the capital G of P and the capital F of P. So the convolution theorem tells us that we find our little f, or I'm sorry, little y, as the convolution of little g and little f. Okay? So here's our g of t. And where's our f of t? Our f of t was right here. It was e to the 2t. Okay, so we have to find the convolution of those two functions. Now remember what we said is that the convolution is commutative. Okay, so the convolution of g and f is the same as the convolution of f and g. Okay, convolution of g and f is by definition the integral of g of t minus tau times f of tau d tau with limits from 0 to t. But we also said that this was equal to the convolution of f and g, which is the integral of f of t minus tau times g of tau d tau, again from 0 to t. So what we said before is since these two are equal to each other, we can put the t minus tau, right? In other words, the t minus tau can be arguments of either function, f or g, and then tau is the argument of the other one. And we said that we want to put the t minus tau argument in the simpler function. Because that'll make it easier to do the convolution integral. And the simpler function between this one and this one is obviously our f. Right? Okay. So that means our y of t is going to be equal to the integral from 0 to t of f of t minus tau, that's our simpler function, so that's what we're going to put the t minus tau argument in, times g of tau d tau. Okay, so plugging in, our function f is equal to e to the 2t, but we're replacing t by t minus tau, so it's e to the 2 times the quantity t minus tau. That's our f of t minus tau. Our function g from over there is we've got a 2 in the denominator, and remember we're replacing t by tau because the argument we want to put in here is tau. So it's e to the 3 tau minus e to the tau. And then d tau. Okay, so let's combine, simplify this before we integrate it. Let's pull the 1/2 out in front. And we'll multiply this exponential through by these, and again, add the exponents. So this first term, this times this, will be e to the 2t. Right? We had 2t minus 2 tau plus 3 tau, so e to the 2t plus tau. And a minus sign from here for the next term, and we have an e to the 2t minus 2 tau plus tau, in other words, 2t minus tau, d tau. Yeah?
Would it be 2 times the quantity of t plus tau?
Well, we've got e to the 2t minus 2 tau, right? We multiply that out. And then from this first term, we add 3 tau. For the second term, we have an e to the 2t minus 2 tau plus tau. Right, so I combine those 2 taus there. That gives me e to the 2t plus tau for that one. And for the other one, e to the 2t minus tau from combining those. Okay, so I think it's right the way it is. Okay, so anyway, so remember that we're integrating with respect to tau. We're treating t like a constant as we do this integral. Okay, so there's a 1/2 out in front. So from this first term here, when we integrate this exponential, we get the same exponential back again. And we would bring down, divide by the coefficient of the tau, which is 1. So that doesn't change anything. Okay? And then minus, from the second term, we again have the same exponential back again. I'm leaving room for a coefficient out here in front. And we bring down the coefficient of tau is minus 1, so 1 over that minus 1. Okay? And then we have to evaluate this at the limits of integration, which are from 0 to t. Okay, so when we plug in the upper limit, tau equals t, this first term will become e to the 3t. We'll have a plus sign, right, because these minus signs cancel. And so from the second term, when we plug in the upper limit, tau equals t, we have e to the t. And then subtracting the lower limit, right? Subtracting because it's a lower limit. So now we're plugging in tau equals 0. So we have an e to the 2t from this one when we plug in tau equals 0, plus, because again those signs cancel. And when we plug in tau equals 0 here, we have and e to the 2t also, it looks like. Just wonder if I did something around here, because, oh no, that's okay. That's right. Okay, so anyway, we're almost done. Right, this is our y of t, so just simplifying slightly, we can write this as 1/2 times e to the 3t minus 2e to the 2t plus e to the t. So that's our solution. Okay, to our ordinary differential equations. And as usual, it's a good idea to check this. It's always a good idea to check solutions to differential equations after you find them. And so, to check this, we're going to have to plug back into, here was our initial differential equation that we started with. So to plug back in and check, we're going to have to calculate y prime and y double prime. So using our result for y here, calculate y prime from that. So we'll have 1/2 times the quantity 3e to the 3t minus 4e to the 2t plus e to the t. Okay, because we bring down 3 in front of this one and a 2 in front of that one. Otherwise, we get the same exponentials back again. And let's take one more derivative to calculate y double prime. So we still got a 1/2 out in front. When we take the derivative of this, we get the same exponential back again. We bring down another factor of 3, so we'll get 9e to the 3t. Similarly here, we get the same exponential back again, but bring down another factor of 2, so minus 8e to the 2t plus e to the t. So therefore, y double prime minus 4y prime plus 3y. That's the left-hand side of our original differential equation. Okay? So let's plug in this for y, this for y prime, this for y double prime into this expression right here. Okay, notice everything has a 1/2 out in front. So let's just leave that out in front. There's a 1/2 out in front of the y double prime, the y prime, and the y. So there'll be a 1/2 in front of every term when I plug them in. So let's pull that out in front. So again, y double prime, we've got an e to the 9, I'm sorry, e to the 3t minus 8e to the 2t plus e to the t. And then we have minus 4 times y prime. So minus 4 times this, I've already pulled the 1/2 out in front, so just multiply minus 4 times what's in here. So that gives us a minus 12e to the 3t plus 16e to the 2t minus 4e to the t. And then plug in 3 times y. So here's our y. We've already pulled the 1/2 out in front, so just multiply the rest through by 3. So that's plus 3e to the 3t minus 6e to the 2t plus 3e to the t. Okay, so let's combine terms here. We've got the 1/2 out in front. Let's look for the e to the 3t terms first. So there's a 9 minus 12 is minus 3 plus 3 is 0. So in other words, those 3 all cancel. The e to the minus 2t term, or e to the 2t terms, we've got a coefficient of minus 8 there, and plus 16, and minus 6.
Just 2.
Yes.
So that gives us a minus 2 e to the 2t.
Plus 2.
Is it plus? Yeah, it's plus 2. Okay? And the e to the t terms, I think, are going to cancel. We've got a 1 plus 3 is 4 minus 4 right there. Okay? And obviously the 2 and the 1/2 cancels here, so we get e to the 2t. And that is exactly what the right-hand side of our differential equation is, so it works, right? This is exactly what we expect. And furthermore, we can also check our initial conditions, or our boundary conditions, right? According to the initial conditions, both y naught and y prime naught should be 0. Let's check that as well. Right, y naught means y evaluated at t equals 0. Here is our y right here. So this is 1/2 times e to the 0 minus 2e to the 0 plus e to the 0, right? When we plug in t equals 0. Well, e to the 0 is 1. Right, so this is 1/2 times 1 minus 2 plus 1, which is complete 0. And similarly, y naught prime, in other words, y prime evaluated at t equals 0. Here's our y prime, so let's just plug in t equals 0. So we have 1/2 times the quantity 3e to the 0 minus 4e to the 0 plus e to the 0. In other words, 1/2 times 3 minus 4 plus 1, which which of course is 0 also, as expected. Okay? So everything works. Our solution, when we plug it back in, it's clearly a solution of the differential equation, and it met both of our boundary conditions. Okay? So that's an example of how we can use the convolution theorem to help us solve differential equations. Remember, we use table entry L7 in this case. And when we were finding this function capital G of P, remember we originally got it in this form, and our next step was to factor it and to look at what these A and B's were. In our case, A and B were not equal to each other. That meant that this was of the form of this here, which is what's listed in L7. So L7 was what we used to get our little g of t. Like I said, if A and B turned out to be equal, L6 would have been the table entry we would have used instead of L7. Now remember that this was all for boundary conditions when both y naught and y naught prime were equal to 0. If we have different boundary conditions other than those, right, something other than y naught and y naught prime equals 0. We have, let's say, maybe different non-zero values of these instead. Then obviously there'll be a little bit of a change. Right? When I plug in from L35 here, I'm going to have some additional terms that I didn't have in the example I did. And so that's going to change the form of your G of P. It's not going to look like this anymore. Right? And so L7 and L6 will not be the useful ones in those cases. Often L8 and L18 will be useful. Okay, to find your little g of t. But otherwise, it's pretty much similar to the example we just did. Okay, so I guess we're out of time. So let's stop there. Like I said, there is also a convolution theorem for Fourier transforms, but I don't think we're going to have time to talk about it, so don't worry about it. What we'll do on Monday, remember we still do have class on Monday, is we'll talk about something called the Dirac delta function, which is useful in a lot of physics applications. You'll see it in your upper division physics classes for those of you who are physics majors. And we'll talk a little bit more about the convolution also, because I want to talk a little bit about some of the physical applications of convolutions, what they're good for other than solving differential equations like we did today. They do have other applications as well. And we'll talk about those. I think it will help when we talk about the Dirac delta functions first, because then the other discussion will make a little more sense.
What should we start studying for the final?
You should start studying everything we've done for the final. I have put a sample exam on Blackboard, so it contains some examples of Fourier series and Fourier transform and Laplace transform type questions. So take a look at that. You obviously should still know some of the stuff we talked about earlier in the quarter, the vector calculus. So Green's theorem, Stokes' theorem, divergence theorem, all of those things are important. Gradients, curls, divergences in the various different coordinate systems. So, take a look at that also. Study the midterm exam, study the earlier homeworks to look at that material. I think you can assume about 40% of the exam will be on the material from before the midterm, so the vector calculus stuff basically, and about 60% will be the material after the midterm. So that's all the Fourier and Laplace stuff. Okay.
How many problems are we looking at?
So 5 problems, but I think there's one that's a bit long, but the others are all fairly short. So I know it sounds maybe like a lot of problems, but I don't think it'll take you any more time than the midterm did. It might take you less time. So 5 problems, like I said, you can do the final on either Wednesday or Friday. Wednesday would be at our usual 10 to 12 time. If you want to do it on Friday at about 1 o'clock, just let me know, and you can do it either time.
Could we do it during Whitney's time slot of 2 to 4? Or
On which day?
on Friday as well? She kind of blocked us out that time.
Oh, she did, because she and I discussed it, and
Oh,
I,
I'm sorry.
4 to 6.
I'm speaking incorrectly. It's 4 to 6.
on Friday,
Yeah.
I will have to check my schedule. I'm not sure if I'm available quite that late in the day or
I don't want
not.
to keep you here that late.
Okay, but let me check. Okay,
Okay.
I'm perfectly happy to do it if I can. So let's just say at this point, if you want to take it Friday afternoon, let me know, and we'll leave open the time slot. And maybe not everybody can come at the same time. That's fine. I'm willing to stay a little bit longer if need be. But let me just check my schedule because I'm not sure if I'm available, from 4 to 6 or not. But I'm definitely available earlier. Like I said, if you want to start at 1 or 2 or something like that. And remember, we do have class on Monday. That's when we'll talk about the Dirac delta function. Okay?
It's also called the impulse function,
Yeah, sometimes.
I've heard that thrown around.
It's often used to describe, like a force that is an impulse. In other words, a very large magnitude force, but that lasts only for a short duration of time. It's used as an approximation for that. It basically corresponds to something like an infinite force, but over a period of time that shrinks to 0 in some kind of way.
Lots and lots of work.